Yeah, and you can do even more with the amplitude, which is then called scaling or amplitude scaling. It's the same as before, that we do an offset translation, do a shifting with the mean, but in addition do also a scaling. Yeah, and how can we do the scaling? Well, typically by dividing it or normalizing it in the usual case with the standard deviation. So SQ is the standard deviation. So it's the same as before, but the shifting is followed by a scaling through the standard deviation. So and that helps if time series have similar trends but different amplitudes. Yeah, you see that here the blue one here goes up with a small bump here, and then goes down in a valley and goes up again and then goes down again. Yeah, and the green one also, even though it goes down here, goes up here with a clearer bump here. It goes up again, goes down in the valley, goes up, goes down, and so on and so on. Yeah, and if we just shift it, that's not enough, because the amplitudes, the degree of the amplitudes, or the magnitude of the amplitudes here is different. And if you, again, application specific, want to somehow remove that different scaling, you need to apply scaling afterwards, obviously. Yeah, so in that case, the same as before, you do the shifting with the mean in both cases, with all time series actually, and also do the scaling using the standard deviation. Yeah, so that is called normalization, which is typically meant that we do shifting and scaling. And you see the result if you do shifting and scaling, which is the blue and the green one here. Now they have mean in both cases is 0 again, and also the amplitude is now scaled. So it's the amplitudes are somehow comparable. Yeah? And once again, I think it's clear that it's extremely application specific if you really want to work on the raw data, or here on this scaled and so on the normalized data actually. Yeah? So it's very, very application specific. And another one that we want to show you, among many other things, is trend elimination, at least linear trend elimination. Yeah? And that is good if you have similar time series, but they have different trends. You know? So you see here, the green one here, the blue one here, they have a kind of similar behavior, but they have a different trend. So the green one has a positive trend, and the blue one has, so to say, a zero trend. Yeah? And well, if you somehow want to get rid of this positive trend of the green one here, then you can determine the regression line and move each time series by this regression line. Yeah? Of course, that gets a lot more complex when object features when an object features more than one trend. Yeah? So here is just one trend. If the green one would have, first of all, a positive trend and then a negative trend, or two different positive trends, that's a little bit hard then to remove, because you would know how many regression lines do you want to have and stuff like that. Yeah? But I think the idea is clear. Yeah. So if you want to eliminate these linear trends, then you just determine the regression line and move the particular time series objects by these regression lines. So you see here the difference. Here in that case, it's just offset translation and amplitude scaling. Yeah. So these two different things are still not the same, or still not similar. So here it's offset translation plus trend elimination, and you see that basically the green and the blue time series have more or less the same shape, but you cannot see that here in the raw data, obviously. And once again, it's extremely application specific if you really want to remove the trend or not. Yeah, maybe you have a sensor which has weird behavior, introducing kind of trend or whatever, or something else, I don't know. Yeah? Then it could be interesting to do trend elimination in that case. Yeah, and last but not least, what we want to show you is noise reduction. Yeah, so in that case, we want to have similar time series and reduce noise. So we may have similar time series with a large noise portion. And what we can do here is so-called smoothing, which is a normalization over a range of values. So typically we use a sliding window, so a window of k or 2k adjacent values, and we aggregate these the values in the sliding window by just one value. Yeah? So for example, we replace the ith value with the mean value of the 2k adjacent values in both directions k. Yeah, so we have maybe this this thing here, and we look in both directions for k values, and then take the mean value of all those 2k values and replace this particular thing by this mean value. Yeah, and we get a smoothing of the raw data. So that is the raw data that is after smoothing, sorry, after smoothing, and you see again, the trends and the shapes that they are similar, much better than here, of course. Yeah, and here, if you would apply some similarity functions or distance measures, you will probably get a larger distance, a much larger distance than here. Yeah, because you have all these outliers and noise things here at the amplitude, and here there is no noise, no outlier in that case. Yeah? So that can be important if you have a lot of noisy sensors actually. Yeah? So if you work in construction, for example, if you use a lot of sensors maybe for electricity and stuff like that, you very often have a lot of noise, a very noisy signal. In that case, it could be good to do a smoothing, and you can do smoothing in many different ways. So this is just one way to do it, using a sliding window, yeah, which is one of the classical way to do it, but you can do it in different ways. Yeah, and there are maybe many more types of distortions that might be of interest, and that might where you think it is good to remove them. Extremely application specific, once again. Yeah, so all this stuff here we talked about here in this subsection is not that you should do it all the time, but you should really think about what to do in pre-processing. Think about the shit in, shit out problem. So it's really driven by your application, and you really should think about it very carefully. And just that you see how different pre-processing steps, or pre-processing steps at all in that case, could really help is, so this is one of the famous pictures from this tutorial by Iman Kio. So yeah, you have some raw time series from 3 classes. So you have the red class, the green class, and the blue class. You somehow see, if you closely look at those, that they have a very similar shape, but not too similar, and a lot of noise and stuff like that. So if you just try to cluster those things here with the raw data, actually, with maybe Euclidean distance or stuff like that, you see that you get somehow what we say in German Kraut und Rüben, so not fish, not meat, so to say. Yeah, so you get a lot of, so not very homogeneous, a very heterogeneous clustering. Yeah, so you cannot really reproduce the original labels, red, green, blue, in those clusters here. Yeah, so there's no clear clustering structure, and even if you try to do, there's no clear homogeneous clustering structure to reproduce these class labels here. If you do noise reduction, trend elimination, scaling, and normalization, you end up in these data sets here, or in these time series here. And then if you do signaling clustering, you see that you pretty good end up in 3 clusters. This is one cluster here, this is one cluster here, and this is the 3rd cluster here. And these 3 clusters are extremely homogeneous, perfectly homogeneous in terms of class labels. Yeah, so you get one cluster with only the blues, one cluster with only the greens, and one cluster with only the reds. Yeah, and so that should tell you that in this case, once again, application dependent. So in this case, it really works very well. So always consider to do pre-processing. So look at your data first. That's very important if you work with time series. So look at the data first. Think about any pre-processing things that you should do. If it's very noisy, if you have different trends and stuff like that, then it's a good idea to do that. And you know some examples, what you can do, and of course there are many more. Just that you know. Okay, so that was pre-processing. We will have one more for this week, the similarity models for time series, coming up in the next podcast for this week. And then we stop after 3.3. Okay.